up just a pound of propellant. But it's very, very efficient. And in fact, I brought a prop here, and I'm going to show you how to do an ion propulsion experiment at home. That is, the ion thruster pushes on the spacecraft as hard as this single piece of paper pushes on my hand. So it's fantastically gentle. But over time, the effect of this thrust can build up. So instead of thrusting like most planetary spacecraft do for a few minutes at a time with its engine, a thruster like this will operate for months or even years at a time. And gradually the effect of this thrust will build up. It would take a spacecraft like Dawn 4 days to go from 0 to 60 miles per hour. So it's not exactly a hot rod. But we don't thrust for 4 days. If you imagine thrusting for 40 days or 400 days or 4,000 days, you can build up to fantastically high speeds. And so it's what I like to call acceleration with patience. And as an illustration of the benefit of the ion propulsion, by being so efficient, being so parsimonious in its use of propellant, JPL has a number of spacecraft in orbit around Mars. There's even a model of one back there. And when these spacecraft get to Mars, they have to execute a burn with their engine to be captured into orbit. And a maneuver like that typically may consume something like 280 or so kilograms. That's about 600 pounds of propellant. And that's propellant that you and I, as taxpayers, have to pay to lift off the Earth on a rocket in order to get it out to Mars. Well, a spacecraft like Dawn with ion propulsion could execute the same maneuver using just a little more than 20 kilograms or less than 50 pounds of propellant, a substantial savings. On the other hand, the Mars missions make a maneuver like that in maybe 20 minutes or so, and that's enough to change their velocity by about 2,000 miles per hour. A spacecraft like Dawn would take 3.5 months to do it. But if you have the time, and I do, I'm not in a hurry, then it's a really efficient way to travel around the solar system. And so this is really the key to enabling a mission like Dawn. Now, I mentioned that the ion propulsion has been around for a long time. There's some people who believe that it's been around a very long time. I'm not sure that's actually really true, but the first mission to really get off the ground with it is Deep Space One, which you heard about in the introduction. And the primary purpose of Deep Space One was to test high-risk advanced technologies like ion propulsion so that science missions like Dawn could use them with confidence, so that the people working on answering the scientific questions wouldn't have to solve the many engineering questions associated with using a new technology like this. Excuse me. So Deep Space One was launched in 1998. It had a very successful mission testing the technology. It also went on and conducted a very successful science mission of its own. Turns out that mission is perhaps not as well known as many others because it achieved its accomplishments in September of 2001 when news was focused on other topics. But for the purposes of this talk, what really counts is Deep Space One having tested the ion propulsion. Excuse me. So shortly after it was launched, it extended its solar arrays. We checked out the spacecraft, and as it left the Earth and Moon behind, turned on the ion propulsion system and checked it out, understood how it worked, and solved all of the problems that would need to be solved for a subsequent mission to count on it. And we ended up thrusting with the ion propulsion system on Dawn for about 680 days. So the longest powered flight ever conducted. But that's an artist's concept. I wanted to show you my favorite photograph of the spacecraft. This is a picture taken with the famous 200-inch telescope on Palomar Mountain, and that's Deep Space One. And this picture was taken when Deep Space One was 9 times farther away than the Moon is. And this streak here doesn't tell you anything about the shape of the spacecraft. The reason for that is the telescope was tracking the stars, and of course the spacecraft had its own independent motion through the solar system, and so it smeared out a little bit. And I personally, again, this is my favorite picture of the spacecraft. I think it's really cool that humankind can send spacecraft deep into space, out into the cosmos. And I think it's also cool that we can get pictures of it. And this sort of thing is not just the product of the people at JPL and its collaborators who were fortunate enough to work on it. In my view, this is a product of humankind. I think everybody participates in something like this, and I personally think it's very inspiring and really exciting. And at the time this picture was taken, just to give you an idea of how distant and faint this little spacecraft was, this is approximately visual magnitude 22.5 for you astronomers, and for the rest of us, it means it's about 4 million times fainter than what you would be able to see with your naked eye. So I think that's a pretty cool picture. So now let's get back to Dawn. This is the spacecraft, and it's going to do the TIE fighters one better because it has 3 ion engines. Here's one here, here's a second one, and there's another one on the back. Large antenna, which will be used to send the scientific information back from Vesta and Ceres to Earth. And large solar arrays, which, as on most spacecraft, convert sunlight into electricity. That electrical power is used to operate the ion propulsion system and the rest of the spacecraft. And these solar arrays are really huge. The full extent here from tip to tip is almost 20 meters, or nearly 65 feet, which, as some of you know from the beginning of the when we were getting set up here, 65 feet is the distance from the edge of the screen here to the back corner of the room there. And for those of you who are watching this in the webcast, it's wider than your computer screen. So this is going to be the largest span of solar arrays for any spacecraft that NASA has ever sent into the solar system. And the reason it's so large is because the ion propulsion system is very power hungry. It needs a lot of electrical power. And we're sending the spacecraft far away from the sun, where sunlight then is not so abundant. And so when it's out at distant Ceres, these arrays still need to produce enough electrical power to operate the ion propulsion system as well as the rest of the spacecraft. So let's take a look at some photos of the actual spacecraft instead of the artist's concept. Here it is in its assembly facility at Orbital Sciences in Virginia. Here's that same large antenna now with a covering on it that's used to control the temperature when it's out in space. And the solar arrays are folded up here so that they'll fit inside the nose cone or the payload fairing of the rocket. And on top here are a number of scientific instruments and engineering subsystems. Down here at the bottom is one of the ion thrusters. We can take another close-up look at that. So here's the actual thruster, and there are about 15,000 little holes in this 1-foot diameter grid, and those are the holes through which the xenon will be accelerated. And it sits on a support structure here, which allows the spacecraft to tip and tilt the thruster to point it in the direction that it needs. And I think people often sort of forget that, you look at a spacecraft and it kind of looks cool on the outside, but there's a lot of stuff inside to make it work. Just shows this one view, which has a lot of cabling and other systems, but mostly what you're seeing here is a subset of the plumbing that's required to get the xenon from the tank, which is inside here, to the thruster. And before I go on to the next picture, I want to point out that I told you that the ion propulsion system comes from what we have experience with Deep Space One. Much of the spacecraft design, both the structure and the electrical systems, come from other spacecraft that Orbital Sciences Corporation has built. And by taking advantage of designs from previous spacecraft, again, it saves you and me as taxpayers some cost. But I want to get back to the xenon now and show you a photograph of xenon. This is actually my pet chameleon, Xenon, and he, I think, has a sort of a personal interest in ion propulsion for, as you can see, cosmetic reasons. This is, again, another view of the spacecraft. Here it is in the background there. Here's this big antenna, which doesn't have the cover on yet, just to give you a sense of the size of the solar array.